the complement of a set A, denoted by A prime, this one, is the set of all elements of the universal set U that are not elements of A. For example, we have a universal set 0, 2, 3, 4, 6, 7, 17, and we have M as 0, 4, 6, 17, and P. So let's find M prime, or the complement of M, and the complement of P. So the complement of M, since M is 0, 4, 6, 17, these are the members of the set that is on the universal set, but not on the set M. Okay? We have 4, 6, 7, 0, 4, 6, 17. So all you have to do is to pick these numbers, 0, 4, 6, 17, and let's choose the numbers that are not chosen, which is 2, 3, and 7. So again, complement means that these are the members of the set that is present on the universal set U and not on the set itself, right? So from M, 0, 4, 6, 17, so not included on the M, but is present on the universal set, are what are considered as the complement of M. So 2, 3, and 7 is a set, is the complementary set of M. Now for P, we have 0, 3, 0, 3, 7, and 17, because we have here that X is an element of even natural numbers and is less than 7. So what are those numbers? We have 2, 4, and 6. Okay? So those are the members of the set P. Even natural numbers, which means that are positive, and is less than 7. So those are 2, 4, and 6. So let's choose 2, 4, and 6. What's left on the universal set are 0, 3, 7, and 17. So this is the P prime, or the complement of P, that is 0, 3, 7, and 17. So the complement of the universal set and the complement of the empty set. So U prime is equivalent to the null set, and the complement of the null set is the universal set. Set A is a subset of set B, denoted by this sign here, if and only if every element of A is also an element of B. So that is subset. So let's determine each statement if it is true or false. So 5, 10, 15, 20 is a subset of 0, 5, 10, 15, 20, 25, 30. So are these members present on the second set? Let's check. So 5, 10, 15, 20. So all of these elements of the first set are on the second set. So therefore, this is considered true because the first set is a subset of the second set. Alright, for number 2, we have the set of counting numbers is subset of the set of natural numbers. So what are the counting numbers? These are 1, 2, 3, 4, 5, and so on. And then the set of natural numbers are the ones that are positive integers. So 1, 2, 3, 4, 5, and so on. So therefore, this is true. How about number 3? Null set is a subset of the universal set. That is also considered as true. Set A is a proper subset of set B, denoted by this symbol here, if every element of A is an element of B and A is not equal to B. So let's determine first number 1. A, E, I, O, U, and then E, A, O, U, I. Okay, so all of the elements of the first set are on the second set, but are they equivalent? Or are they equal? Sorry. So the first set is actually equal to the second set. Therefore, this is not considered as proper subset. This is the criteria that must be met, enabled for us to consider a proper subset. So the first set is not a proper subset of the second set. How about number 2? Mars, Venus. That's the first set. And then we have Mars, Venus, Jupiter, Earth. So are these elements present on the second set? Yes, it's true. Next question. Are the two sets equal? No. So we can conclude that the first set is not equal to the second set. Therefore, Mars, Venus is a proper subset of Mars, Venus, Jupiter, Earth. So find the complement given U as 0, 1, 2, 3, 4, 5, 6, 7, 8. So how about number 1? We have 2, 4, 6, 7. So again, complement means that these are the members of the universal set that is not present on the given set. For example, 2, 4, 6, 7. So let's identify 2, 4, 6, 7. And what's left are 0, 1, 3, 5, and 8. So the complement of number 1 is 0, 1, 3, 5, and 8. So that's the complement of number 1. How about number 2? It's the null set. So the complement of the null set is the universal set itself. The whole set. So 0, 1, 2, 3, 4, 5, 6, 7, and lastly 8. So that's the complement of the null set. Number 3, the set of odd counting numbers less than 8. So what are the odd counting numbers less than 8? So we have 1, 3, 5, and 7. So what's left are 0, 2, 4, 6, and 8. So this is the complement of number 3. Let's insert either a subset or not a subset in the blank space between the sets to make a true statement. Red, white, blue is a subset or not a subset of the colors of the Philippine flag. So this is a subset of the colors of Philippine flag. Number 2, null set is blank of A, E, I, O, U. So actually, null set is a subset of A, E, I, O, U. All sandwiches is not a subset of all hamburger. The intersection of sets A and B, denoted by the symbol, is the set of elements common to both A and B, and the union of set A and B, denoted by A, U, B, is a set that contains all the elements that belongs to A or to B or to both. So take note of the difference. So let's have we'll be having an example later. Okay. So given D as 0389, E as 348911, F as 0268, and G is 2. Let's find the intersection E. So let's consider D and E, sets D and E. So what are the elements that is present on both D and E? So first we have 3. Next we have 8. And we have 9. Therefore, the intersection of sets D and E is 3, 8, 9. How about the intersection of D and F? So we have 0, and 8. So this is the intersection of D and F. So the elements that are present on both sets, that's the intersection. How about E union F? So we have E union F. So all we have to do is to combine all the members of the sets E and F. So we started with 0, 2, 3, 4, 6, 8, 9, and 11. So that is union. So we'll be combining all the members of the two sets. That's union. Then we have F union G. So we'll combine them. We have 0, 2, 6, and 8. So that's the difference between union and intersection. De Morgan's law. For all sets A and B, A union B complement is equivalent to A complement intersection of B complement, and A intersection B complement is equivalent to A complement union B complement. So this is the De Morgan's law. We can express a union in terms of an intersection. So we'll just have to get their complements, and vice versa, from intersection to union. So that's De Morgan's law. We have properties of sets. You have commutative. A intersection B is equivalent to B intersection A, and A union B is equivalent to B union A. And we can also do associative properties and distributive properties. All right. So let's draw a Venn diagram with each of the following elements placed in the correct region. So number 1, 2, 4, 6, 8, 10, 12, 14. That's for the universal set. A is 2, 10, 12. B is 4, 8, and C is 6, 8, 10. So for number 1, the solution is, first, let's make a universal set. Then let's say this is A. Okay, this is A. And we have B. So is there an intersection between A and B? No, they don't have the same elements. Therefore, let's separate them. And that's B. How about C? C is an intersection with A and B. Okay, so this should be the C. All right. And then what is the intersection between A and C? We have 10. So their intersection should have the element 10. And how about the intersection of B and C? So B and C. So they have 8 as intersection. So we'll place the element 8 on their intersection. Then what's left on the C is 6. So 6 should be on the C. How about A? So we have 2 and 12. So therefore, 2 should be here, and also 12. Then 8. B has a remaining member of 4 because 8 is the intersection of 6. So that's where the numbers will go. And lastly, the universal set. So we have 2, 4, 6. So 2 is already on the A, 4 is already on B, 6 is already on C. 8 is already on the intersection of B and C. 10 is already on the intersection of A and C, while 14 is not yet present on the Venn diagram. So therefore, we'll just place here because 14 is neither located on A, B, or C, so it should be on the outside. So that's how you express sets in Venn diagram.